Fantastic. And I think I'm doing a very good job of keeping time, which is not necessarily a given with me. So well done me. Final talk of this session, we have Darren Burns, who is going to talk about models for scalable treatment of sequencing in HTA.
Okay, how do I get my slides on? Yeah.
I think that's the only way that's going to work.
It'll be fine. If I do something like this. That'll do, right? Is that all right? No, I'll hit that. Yeah, that makes sense. All right. So I'm going to hide behind my script like a coward. And I've used my first page as my parking permit, so that's gone. So I'm Darren Burns. I'm going to talk to you today about a really small package that I built along with Tristan and Dawn from Exeter. In a standard Markov model, individuals move between health states, let's say sick or dead. And the probability of moving to another health state usually depends on only the current state. So in a totally basic Markov model, this is called the memoryless property. That just means that you use the same probability every model cycle. Minor extension to this is to have time varying transition probabilities. These depend on the time since the beginning of the model. A bit like standard partition survival model is what that ends up looking like. This is referred to as wall time in sort of technical world, or time from baseline in our sort of modelling sphere. However, wall time isn't very useful for modelling subsequent health states, as more often than not, how long a patient has been in that particular treatment line is by far the most important determinant of how quickly they exit it. Tunnel states are often used to get around this limitation. They divide a single health state into a sequence of substates that represent time that patients have been in the state for. The term for this is sojourn time, which roughly means time spent away or time on holiday. It's actually the same term that's used in survival analysis for the time that nothing's happened to a patient. Patients are held inside these states and are forced to travel along them, a bit like going through a tunnel, hence a tunnel. Here there's a nice little demonstration of what 50 tunnel states looks like in sequence. And at the bottom, that's what it feels like as a modeler. So why make a package? A couple of years ago, NICE commissioned Pentag to build a model that could properly handle cohort-level sequence modeling to basically any number of treatment lines with a load of flexibility built in. And Pentag brought me in to help out, just kind of build the model engine. Tristan one day explained to me that you could handle all of this with matrices, and it went completely sailing over my head. I had no idea. Eventually, after a bit of slowing down trying to think about it, I got to understand how it works and realised it's actually a little bit simpler than you might think. It turns out when we did it in that project, the way that we did it, it was actually really easy to just generalise it to a wide number of applications with a couple of cheeky additions that make it useful outside of just oncology. So why not make a package then? Last thing to say on this one is I've actually done, I've been involved in 2 of these for NICE in the last 3 years that do this. So they do happen, there is a need. All right, top level math. You can do tunnel states with matrix algebra, hooray. But the problem is they get massive really fast. You can arrange the transition probabilities in kind of like a slide, as my friend Simone always called it, like a slide that people go down. But what you can also do is put in vertical strips of transition probabilities in blocks along the matrix. And that is the probability of going to the start of another tunnel state, which is kind of cool. Lastly, you can break up matrix multiplications into little pieces if you need to. What are you on about? This is important. So, Markov modeling. Usually a Markov model in R uses a list or a 3D array containing some transition probabilities and uses matrix multiplication. That's what that little sign there with an arrow on it means in R, to basically do the multiplication. So that little line of code there, that's a whole...
Darren, could you move your microphone a bit?
Oh, am I too quiet? Don't usually have that problem.
We can hear you, it's just online.
Treat Seeker does exactly the same thing, but adding in tunnel states and using a sparse matrix. So that M at the bottom there that's being slightly cut off is a really, really big matrix. But it's something that's called sparse. Right. Before I move on and talk about the package, it's time for a little soapbox moment. Packages should be scalpels, not hammers, and should be small and contained enough that we can apply them to a specific context or indeed ditch them without any consequences if we think it's not the right tool for a particular task. Even the biggest packages like FlexServe focus on doing one thing. That handles survival regressions really nicely. Frequented survival regressions. And it does it really well. It's not related to health economics. It's not related to cost effectiveness modeling in any way, but it's still incredibly important and useful for it. And it's become a central part of what we do when we use R for health economics. But it does one job. Cost-effectiveness modeling is not one job. It's loads of different goals, skills, ways of working, strategy, constructivist thinking, etc. Because of that context, it's far more useful for us as modelers to have a toolbox we can cherry pick from than to sort of being precluded from using one particular toolkit because we didn't do one thing in a particular way. People doing cost-effectiveness modeling of R-HTA stuff have also, in our area, especially in this group, have little territories that we really care about and we want to make better for everybody. Can't we use that to sort of build something up from the ground? All right. Leave it alone, Darren. Okay, so why is this useful? There are more and more sequencing models, and the treatment pathways are getting more and more complicated, yet there are loads of early line treatments, like in multiple myeloma, renal cell carcinoma, a few others that have 5, 6, 7 treatment lines, loads of subgroups. On top of that, follow-ups are getting shorter, meaning the OS lines that we see, the overall survival Kaplan-Meier that we see, is both less informative within the first treatment line and less informative overall, and probably biased. This leads towards 3-state partition survival models essentially becoming redundant over time because their results are just going to be completely unrealistic and we can't adjust for them. Because this makes something that's really fiddly, this package, makes something really fiddly and annoying to implement just a lot faster and easier, it's a huge gain without it trying to do anything else. The other thing I like is because it's a standalone tool, you don't have to build a model around it. You can just use it to QC your implementation. If you build a patient-level state transition model that does this, like I did for NICE last year in VBA, well, I would have loved this package to be able to say, have I done it right or not? Okay, so modeling workflow. Obviously, this package completely disassociates itself with the stats being correct because it's there to do one job. So you're still going to need to get stats for 5 different treatment lines for 10 different populations. There's going to be a really big task, and there's going to be loads of ITCs, and so it's really difficult. But when you get there, if you're also faced with a really difficult task of building a model that's extremely error-prone, then it just makes it 10 times harder. Wouldn't it be nice if we could just bungle the transition probabilities in and get a trace? So even if we do need to recode something in a different software, we can just do it and we know the answer from the beginning. Hooray. So, methods. Right. This is supposed to be a joke, okay? Right, so now that's clear. Let's move on. No, it's not clear. So the way it works is you kind of break up the calculation. So in the top here, these would be your kind of first line PFS bits. And they would change every model cycle, and that's kind of handled separately in this package. And then you get these really big kind of strips that go off diagonally like this, and then you have vertical bits. And that's it just kind of boils down to just a matrix multiplication, specifically a sparse matrix multiplication, which just means ignore all the dots in there and do a multiplication. That's all it means. Right, so let's do a more colourful one. So, in this example, we've got two fixed duration tunnel states, which are these middle ones here, that go for 3 cycles. So you can see there's sort of 3 rows. But patients can go forwards or backwards in them. So these patients here can go back to the start of this tunnel, which gives us a mechanism for doing something like relapsing and remitting MS without adding any complication to how you program it. You still just put the transition probabilities in. So code, 3 lines for a I don't know, 50-line tunnel state model, which is pretty cool. That's the reason I wanted to build this. So basically, a first line to give it kind of a specification. What are the tunnels? How many states are there before the tunnel sequence starts? Then another one to generate the transition matrix kind of list. You kind of have to give it what's the name of the first state so it doesn't get confused during that. And on the right here, this is just what your list would look like. So it's just got the states there. And then inside it's the transitions to other states. And you'll notice there are ones missing, and it just assumes there's no transitions to those states there. So it just kind of fills in the blanks and then gives you a matrix. And then if there are any blanks at the end, it filters them out before it tries to put them in a giant matrix. All right. Takeaways. It's not quite a page, is it? Right. So this is a small dedicated package to solve a problem that we think is going to get harder and harder over time. It avoids needing to build a patient-level state transition model in most cases. But if you do need a multifaceted patient history tracking, then just make a DES or an STM. You don't have to use this. I'm not saying it's the solution to all problems. It's just a solution to this problem. You can apply this to loads of conceptual models because you can do stuff like a fixed transition tunnel, and then the probability at the end is 0, so it's actually a decision tree node at the end. So you can have tunnels where people are forced to exit the states at the end, and you can just do that infinitely. So basically any model that has a sojourn time, kind of time and state element, you could probably kind of work this. I've written a few vignettes into the package, which I think is worth talking about as well. Because I think it's really nice to do this, especially the vignette that we wrote that doesn't use the package and just does it all from scratch. What it doesn't do is any of the stats, any of the cost effectiveness modeling. It's just a way to get a trace. All right, so I'd be remiss if I went on my high horse ranting about how amazing it would be for all of us to make little packages for specific little jobs, and we can build it all together in a giant daisy chain of love and friendship, if I didn't also talk about the work involved in doing that. Conceptualization was 0. We had to do it for a nice pilot. So we'd already kind of figured out the maths. Tristan had already figured out the maths. First R package for me, so a couple of days kind of figuring out how that works. Generalizing the functions took me an afternoon where I had a really bad cold and I was in bed anyway. The vignettes took a bit more thinking, just like what would be useful for people and not just information overload. So there's a vignette for like building it from, sort of doing this from scratch and how much more painful that is. Then there's one of using the package functions and how easy that is. There's one about fixed duration tunnels, and then there's one about backwards and forwards transitions. It's super small. Doesn't really need much in the way of maintenance, so I think the maintenance would be really low. There's only dependence on the matrix with a capital M package. I think I'll be interested to see what kinds of issues people post. I hope I'm not just grumpily saying user error in response to GitHub issues. No ads planned for it. it's pretty much feature complete at this point because it only needs like 3 or 4 functions total. Some wacky ideas, like multiplying the whole matrix tunnel by like an SMR at a global time point would be kind of interesting. Because then you could layer on wall time onto Sojourn time, which would be kind of adding features. But to be honest, you're pushing the boundary there, and you might as well sort of move into patient level simulation territory. So does it need to do that? And that's it.
Thank you, Darren. Some questions. Howard has one.
Well, this is a question from online. So Rob has shared the link. Are you happy for him to make it public?
Okay.
Repository, yes. Yes, Rob.
Answer was yes. Any more questions? Yeah.
Oh no.
You really are getting your steps in.
Here comes the technical question.
It is a somewhat technical question. So, seeing as you're using sparse matrices, there are plenty of C++/Fortran accelerated BLAS libraries for this. Are you using any of those, or did you do this all yourself?
That's exactly the library we're using. It's matrix with a capital M.
So online people wouldn't be able to.
I'll say that again. Yes. The package we use for this is called Matrix, but it has a capital M on the beginning, which for some reason means it's the C++ one. It's basically a bridge to the C++ library for matrix algebra.
Yes, one more.
This won't be a technical question, Darren. I'm not going to pretend I understood any of that or most of that. My question's on the plot that you showed with the colours. So I think the example that you used was relapse remitting MS and kind of sending people back to a better health state. So i.e. when you get into remission, you kind of go back. I suppose one thing that I'm working in kind of kidney disease at the moment, something that maybe this could work for kind of sending people back to previous health states. So things like when you get to transplant health states and therefore you've got essentially got a new kidney. So how do you model those? And traditional models at the moment they just keep them in a kidney transplant health state. Yeah. So maybe it could be worth you looking into some of those kind of chronic high burden organ manifestations like kidney disease, liver disease, where they get transplants. It wasn't really a question, I suppose. But.
Yes. No, yeah. It's good. Originally, when I did this, I was thinking, should I do like some surgery, some resection surgery, keep it in oncology? But then I thought, well, it just makes sense in loads of conceptual models, and it solves a problem that's really fiddly and very prone to error in Excel models, especially when it's got these backwards things here. That just makes it like, yeah, for me as well. I had to think about this. I was like, can't you just put these transitions like over here? What does that do? And then I tried putting a loop together, and I was like, people are going round in circles. That's useful. That was the extent of the thinking, really.
We have one more online.
Actually, this is a question from me. So Darren, it's really interesting to see that, this may be more a question for Tristram, but the use of sparse matrices and matrix methods that can decompose the matrix. So I've always wondered, is there more use of like block diagonal and techniques that we all remember from university that could be used to speed up models, like where there are subcomponents where patients move around? Like have you and Tristram considered extending this to non-tunnel state cases?
I think it would work.
Thanks. So in the package, one of the things that we already build in straight away is the possibility for you to have some states which don't have tunnels. They only depend on wall time, and so you don't need to expand them into loads of different tunnel states. And so we have like these non-tunnel states, and then what it will do is it will provide you different matrices. So you've got a sparse matrix for all the tunnel states, which is constant over the cycles. That doesn't need updating, so that is quite lightweight to work with. And then you have a component which is generally like a row or two rows, which do depend on time. And so you have a list of those and you pick out the right element from that list in each of the cycles. So yeah, there's a bit of that kind of block matrix algebra that gets used, but generally speaking, just the fact that you've realized this is very sparse and you've used a tool that's for very sparse things gives you a big speed up. Basically, I think to the point where you just don't worry about how can I wrangle this into being wall time dependent. Just say, I'm going to use tunnels and it'll be fine.
Thank you.
That's 50 treatment lines, and it calculates instantly. So that's the scalability. Is just for a laugh, I decided to do 50 treatment lines, and that's with a Markov model with I only did 60 cycles because I wanted you to be able to see the graph, but it kind of illustrates that just calculates instantly. I thought I figured it might be funny if I did 1,000 and the key went like off the, but then I thought that was a bit too far.
It probably was. All right, so let's thank Darren once more.